So now that we've talked about all the different ways that we can start to kind of determine the concentration of our solutions, let's dig back into colligative properties. We said that colligative properties are just any property that will change, either increase or decrease, due to the number of solute particles present. Whether or not there's particles, if there's more particles present, less particles present, what effect does that then have on a property of a substance? And the biggest ones, the most practical for what we use in our day-to-day life, is what we would call our boiling point and our freezing point elevation and depression. We're actually going to be using this little piece for a lab coming up a little bit later in the unit, but we got to talk about a couple of pieces here. So what we're trying to figure out is, okay, if I add a bunch of stuff into the solution, if I add more attractions, if I think about adding salt to water, sure, why not? I'm adding salt to water, and we often do this when we're cooking, right? Usually it's for flavor, but every now and then you'll hear somebody say, well, I can cook my food faster if I put some salt in there, which is technically true because of colligative properties. So if you add a solute into a solution, you've now increased the number of attractions between your particles. Typically a salt, that would be an ion dipole of intermolecular force. Because there's more attractions there now we have to actually heat it up to a higher temperature. It's gonna do what we call an boiling point elevation to actually get the water to escape from this increase of attraction. And so we no longer boil at 100 degrees, we boil at a higher temperature. And there is a formula to calculate how much of that change is going to happen. Remember that delta means the change of. So this formula is the change in the boiling temperature. And it's going to equal some constant. This would be our boiling point constant. This is going to be available on our equation sheets. You'll always have this value. For water, this is a constant. So Kb, the boiling point constant for water, is 0.515 degrees Celsius molal. More on that here in just a second. Times the molality now of the solution, how concentrated is your solution, times what we call the Van't Hoff factor. And so that I there is actually called the Van't Hoff factor. And all that means is when you put this substance into the solution, how many particles does it dissociate into? The good news is for any covalent molecule or covalent species, your Van't Hoff factor will always be 1. Covalents always stay stuck together, and so their Van't Hoff factor is 1. If it was, say, sodium chloride, table salt that we were talking about, well, that's going to split apart into a sodium and a chloride. Its Van't Hoff factor would be 2. If it was sodium hydroxide, that would also have a Van't Hoff factor of 2. 1 sodium, 1 hydroxide coming off into solution. And this makes sense. We now know the concentration of the whole solution, right? The molality. Well, if we have an ionic species and it's split apart into multiple ions, well, then we need to know how much our total solution's concentration has changed. We multiply by the number of particles that are present. Freezing point is almost identical, but it goes the other way. As particles increase, as you add more solute, your freezing temperature gets lower. Okay, and we do this in the winter. Every winter, we take sodium chloride, sorry, not sodium chloride, calcium chloride, rock salt, calcium chloride, that's CaCl2. It has a Van't Hoff factor of 3. It's got 3 particles it dissociates into. And as a result, it lowers the freezing point, the freezing temperature of our water. So if the temperature outside is 32, we've now lowered the freezing point. Now it stays at a liquid at a lower temperature. And the reason for this, the best kind of analogy I can kind of give you for this, is we've increased the number of particles in the way. The water's trying to get together to freeze into that ice. Got to get those water molecules next to each other. But now we have other particles in the way. It makes it harder for this to happen. And again, that Kf is just a constant. Those will always be provided to you. You just need to know what to do with those values. So let's go ahead and take a look at an example here. There's actually 2 here. So we're going to determine the freezing point, what's the new freezing temperature, and the boiling point for the following, given the following constants, and then a couple of questions. I'm going to run through number 1 with you guys, just so that we're feeling okay, and then I'll leave number 2 for you. The answers are available here for us to check as we go as well. So here we go. I went ahead and made a new slide, so we got a little more space. Hopefully I don't run out like I've been running out on all the other ones here. Cool. So let's take a look at this one, make sure we're feeling okay. Again, we've got some constants. Those aren't ever going to change, but we need to know, first of all, for this organic molecule, our Van Hoff factor? Well, good news, it's organic, which means its Van Hoff factor would equal 1. It's going to stay stuck together. It does dissolve. It's going to have actually that OH. It's going to have some hydrogen bonding with the water, but so it does dissolve, but it stays all stuck together. And we need a couple other pieces. We need I guess which one? Let's do the freezing point first. I think that's what the question asked for. For that, we need to know the Kf, which we do. It's up above. We got that 1.85 degrees Celsius per molal. And then we also need the molality. Well, remember that molality, we've been practicing this. Molality equals your moles of solute over your kilograms of solvent. Well, we got to do a little work here then. We've got 120 grams of our substance. We got to change that into moles. So we'd start by finding the molar mass of that ethylene glycol of antifreeze. So I think we go to the periodic table, we add them all up. We've got 62.068 grams per every 1 mole of glycol. We do this math real quick and we end up getting the total moles of our solute. We got 1.9 moles of our solute. Cool, we got moles. The other piece we need is kilograms. We got grams. We're going to move our decimal over 3 spots. It's going to turn into 0.72 kilograms. Now we got everything we need for molality. We could plug it in separately yourself for our pieces and go, but I think we can put it all together. So if we want to know the change in the freezing temperature freezing, we need to have our Kf, which from above was our 1.85 degrees Celsius per molal. Oh, nope, not per molal, just Celsius molal. Oh, no, yeah, per molal. And we're going to take that and we're going to multiply by the molality, which was 1.9 moles of solute over our 0.72 kilograms. Well, moles per kilogram is molal. That's going to cancel our molal here. So we're going to be left with just degrees Celsius. And then we need to multiply by a Van Hoff factor, which for this would be a 1. When we go through and we solve here, we're going to end up with a delta C, or a degree Celsius. But remember, this is delta T. This is a change in freezing point. When you do all this math, you're going to get a value. For this one, we actually get, I believe it's 4.9 approximately with sig figs, 2 sig figs, I believe, degrees Celsius. Well, wait, temperature of freezing, that's higher than what we started, right? We know that if we have added more particles, that our freezing point will decrease. We want to know what the final freezing point is. Well, water normally freezes at 0 degrees Celsius. We would then subtract by this change value to get the new final freezing temperature. Oopsie daisies. Oh, okay. Did I just lose all my writing? That's cool. So for the freezing point, sorry, we'll set it up here in just a second. Sorry. There it is. Sorry, figuring out the tech here. We end up with then our new freezing point is negative 4.9 degrees Celsius. So we actually have to get it all the way down to negative almost 5 degrees to get that solution to freeze. Cool. Let's go ahead and check our other one here. I'm going to erase just a little bit because I think our setup is almost identical for the temperature boiling. The only difference is going to be our constant. So for temperature boiling, sorry, I'm really kind of using my resources here. For the new boiling, or for the change in boiling temperature, we have a new KB. Our KB now, however, from up above is 0.515. And so now we would plug in our values again to try to solve for our delta boiling temperature. When we multiply here, we end up with a 1.4 value. But again, this is the change in the boiling temperature. Okay, well, normally water would boil at 100. If we've added more particles, we're going to have to get it hotter to get it to boil. So we're actually going to add this value to our original temperature to figure out our new boiling temperature of 101.4 degrees Celsius. So then the question is, well, why can you cook faster if you add some salt to your solution? Well, it's because you've raised the temperature. You now have a hotter pot of water that's going to more rapidly cook your noodles, for example, if you're doing mac and cheese. Now you'll notice that it doesn't change it very much. To have an appreciable amount, you would have to add so much salt that your pot of mac and cheese would no longer taste very well. So as we're thinking about kind of our freezing point elevation, depression, here's kind of the mathematical piece to actually figuring out those values.